Hello from Brussels. I'm Andrew Purvis. I'm the General Manager for the Europe, Middle East and Africa region with the Global CCS Institute. I would like to give a big welcome to our international audience who have joined us for this webinar today. We have attendees from all around the world. In today's webinar, we're going to be presenting the findings of a study to assess the economic viability of natural gas combined cycle power plants with CO2 capture and storage in climate change mitigation strategies, emphasizing the use of renewable energy and natural gas for electric power generation. I just want to cover a few housekeeping issues before we start with our presentation. This webinar will be recorded by the Institute, and we're going to make it available on our website along with the slides in the next few days. Now, let me kick off and introduce you to our presenter, Machteld van den Broek, and our panelists, Professor Edward Rubin and Niels Berghout. Machteld van den Broek is our main presenter for our webinar today. She is a senior researcher at Utrecht University in the Netherlands. Machteld specializes in energy systems modeling and especially investigated the role of CO2 capture and storage in the energy system. Among other things, she's involved in the Dutch CATO 2, which is the second Dutch national research program on CCS. Machteld, welcome to our webinar today. Professor Edward Rubin is a chaired professor in the Department of Engineering and Public Policy and Mechanical Engineering at Carnegie Mellon University in the United States. He's an expert on technology learning and techno-economic assessment of energy systems with CO2 capture and storage, and has published many widely cited papers on the subject. Our final panelist is Niels Berghout. Niels works as a PhD student at the Energy and Resources Group of the Copernicus Institute of Sustainable Development, which is at Utrecht University. His research involves, among other things, techno-economic analyses of CO2 capture in the industrial sector and several other CCS topics such as CO2 pipeline transport and shipping. And he made a significant contribution to the research that we're discussing today. Now, as we go through the webinar, all attendees are welcome to submit questions through the presentation. And you can do this through the Questions tab, which should be visible on the GoToWebinar panel on your screen. Questions will be moderated and posed at the end of the presentation. However, we may not be able to answer all the questions that we get today, but we will endeavor to get through as many of the questions as possible in this session. As I said, the webinar will be recorded and will be available on our website along with a copy of the presentation in the next few days. So now, without further ado, I would like to hand over to our main presenter, Machteld van den Broek.
Okay, hello everybody. Thank you for giving me this opportunity to present our study on the cost effectiveness of natural gas combined cycle power plants with CO2 capture and storage. In the slides I will abbreviate this to NGCC-CCS and I will call it gas CCS to make it easier. The reason we did this study was that we want to stabilize concentrations of greenhouse gases at 450 ppm in the atmosphere, and for this we would need low carbon power systems. And of course it's important to know which technologies play an important role, because you want to know whether in which technologies you need to invest and need to execute pilot or demonstration projects. We also wanted to know this for gas CCS, especially because gas CCS can play two types of roles. Namely, it can function as a baseload power plant, but it could also provide backup services for renewable energy sources. So our research question was looking at the cost effectiveness of gas CCS in these two types of roles. In the base load role, it could compete to different technologies, a wide range ranging from biomass or coal with CCS, geothermal energy. In this research, we focused on intermittent renewable energy sources. I call IRES in the presentation, because this comparison has not been done a lot. We focus on three IRES technology: offshore wind, concentrated solar power, and photovoltaic systems. As backup service, gas CCS would compete with storage technologies like pumped hydro storage, compressed air energy storage, and different types of batteries. We looked in more detail to the lithium-ion, the zinc-bromine, and the Zebra battery, which is based on sodium nickel chloride. We were not only interested in current cost, but also how the cost will develop over time, and especially due to technological learning. The starting points for ours, no sun or wind energy. We compared levelized cost of electricity, the LCOE, and these are the typical cost components in the LCOE. For the contribution of capital cost and fixed operating and maintenance cost depend very much on the capacity factor, how much the technology is used in a year. And then you have the variable operating and maintenance cost, fuel cost, CO2 emission cost, and the extra balancing and transmission cost. And for the CCS, you would also need to include CO2 transport and storage cost. The costs for backup services were included in the system cost analysis. I get back to this. This is an overview of our method, and in the blue boxes you see 4 different types of results we produced. First, we present the LCOE, the current, or in the year 2011, and then we wanted to know the maximum reduction potential of each technology for the year 2050, and that would depend on how much the technology can be deployed at the maximum before 2050. For this we had to look at different scenarios, and then we present the LCOE development over time, so for the year 2020, 30, 40, 50 for particular scenarios. And finally, we show the LCOE of simple systems in order to also include the backup costs. I first present you our inventory of data. And we did a literature review of this data and also contacted different experts. And of course, you find whole ranges of each techno-economic parameter. And we chose some median values to present the base results. These median values were either averages of the input data or could be considered as most representative. We also show results for the whole range between optimistic and the pessimistic values. And also note that specific values may be lower or higher in particular regions in Europe. For example, the capacity factor of PV is higher in Spain than in North Europe. And these are the type of data we collected. We have also, we split the gas CCS up in different components. We looked at the combined cycle cost, the capture unit cost, the compression unit cost, and then all the other technologies I mentioned before. We have CAPEX cost, and the progress ratio for the CAPEX, a specific discount rate for the technology, economic lifetime for the technologies, fixed operating and maintenance costs, and also progress ratio for the OPEX. The progress ratios in yellow, they are really based on historical time series, and the ones in orange on an analog technology. It's the progress ratio for the CO2 capture unit, and that's based on the developments of flue gas desulfurization. For the other technologies, there were no historical time series, or they were too short to really base progress ratio on. These are the other parameters which are important. Of course, the efficiency is of importance, and also for this we have some progress ratio, so that the efficiency can improve over time. Availability factor is an important parameter, is the maximum availability of the technology in a year. And for gas-fired power plants, we found 87%, so we took this as the base load capacity factor for gas-fired power plants. For the storage technologies, it's important to assess, to find their cost, how much they are used, and for a typical storage technology to provide backup services, it would be around every day once, and then 9 hours discharging. So with these first data I can present LCOE for 2011 and the different cost components. On the left-hand side you find the power generation technologies, and on the right-hand side the backup technologies. The power generation technologies, they are also split in base load, the gas CCS plants, and in IRES, which provide intermittent electricity. Gas is of course mainly dependent on the fuel price, which is in this case 7 euros per gigajoule, and the IRES depends mainly on the investment cost and fixed operating and maintenance cost. Their costs are higher, and their error bar or uncertainty ranges are also much larger than for the gas-fired ones. This is not only the uncertainty, but also the geographical differentiation. On the right-hand side you can find the backup technologies, and as a comparison we have gas CCS with a capacity factor of 40%. Pumped hydro storage and compressed air are a bit cheaper, and the batteries are much more expensive and have a huge uncertainty range. Note that in these backup or the storage technologies, the cost to charge the storage systems are not included. Then to assess the maximum reduction, we looked at a few scenarios, and we wanted to look specifically at scenarios in which there was a portfolio to reach the 450 target, so a low carbon electricity portfolios. We found 44 scenarios in the Global Energy Assessment Report and 1 scenario in the Energy Technology Perspectives Report of the International Energy Agency. We present the results for 3 scenarios, a bit the extremes, and that is for a scenario with a lot of IRES, and 1 scenario with a lot of gas CCS, and then a base scenario which is a bit in the middle. The portfolios, they look like this. Here in the left upper corner is the high renewable scenario, and in this case, the amount of doublings of, for example, PV is 7 times up to year 2050, while in here is the high gas scenario. In this scenario, the amount of doublings of PV is only 3 times. And here in the left down corner, there's the base scenario. The gas CCS amount of doublings range from 5 doublings up till 2015 to 7 doublings in this high gas CCS scenario. With this information, I can present the maximum reduction potential. On the x-axis, I have plotted the cumulative capacity in gigawatts, and then you see the LCOE for the different technologies. First, in black, the gas normal power plant, and here is already a lot of capacity installed. So the amount of doublings is low, and the cost reductions is only 15%. I should say that the left points of each line is like the cost in 2011, while the right points is the maximum cost reductions, which could be reached until 2050. The gray lines is the gas CCS, which have a maximum cost reduction potential of 30%. And then you have in orange dotted the CSP and the blue offshore wind. They have a reduction potential of 60%, while PV and yellow reduction potential of 70%. As the same picture, but then for the backup technologies. The pumped hydro storage is here below. It also has the most installed capacity up till now and has a reduction potential, cost reduction potential of 30%. Compressed air also 30%, and the batteries all around 60% reduction potential. Gas CCS with the capacity factor of 40% is again added to compare it with. So I get to the LCOE over time, and for this you also need to have a development of the gas and CO2 emission price over time. We took these prices from the International Energy Agency 450 scenario, and in this scenario it was assumed that the gas price would go down because there would be less demand in a low carbon scenario. As a sensitivity, we also did a higher gas price scenario. And then we made many graphs like this for the different scenarios, and also pessimistic and optimistic assumptions of the techno-economic parameters. I just show you one of those, and this is the is under medium conditions in a base scenario. And you see in the blue line, the normal gas plant cost increase because of the CO2 price development. Gas CCS decreases because of the cost reductions, and they cross over at in the year 2025. The CSP and offshore wind decrease over time, and they get to similar LCOEs in the end of 2050. And finally, PV stays a bit more expensive than those technologies. Well, I didn't show the other graph for all the different scenarios, but I focus now on the results in 2040. This graph contains all different scenarios and the pessimistic up to optimistic assumptions. And well, you see a similar graph as in the year 2011, but the error bars are much larger because of additional uncertainty in the progress ratio, as well as in different scenarios there are different amounts of doublings. I want to focus on the amount of differences in the amount of doublings. You see in the yellow diamonds, we have the scenario with the high renewables deployment, and in this case the IRES technologies are cheaper. In a scenario with less deployment of the IRES, the LCOEs are also significantly more expensive. In red, by the way, you see the CO2 emission costs. Also, with the backup technology, the same applies. When there is more IRES, we expect that there will be more backup technology, so more deployment, and in this case, also the backup technologies will be cheaper. In general, NGCC-CCS pumped hydro storage is also here cheaper, and compressed air is well in the same level but has a more uncertain cost range. And then we've also included the backup services, because up till now only the extra balancing and transmission costs were included in the LCOE. And for this, we designed 4 simple systems. Of course, we realize that the real systems will exist out of many technologies, 10 or more. But we think that these simple systems with a few technologies still give a good indication of what would be the cost of having the backup. We designed 4 systems, one with gas CCS, one with IRES and as backup gas-fired power plants, and then one with IRES and backup gas CCS, and one with as backup energy storage. The systems look like this. This is the contribution of the different technologies to the electricity demand. In the first system, all electricity would be produced by gas CCS, and its capacity factor would be 58%. And this is lower than the maximum availability because you have to follow a load pattern of the demand. We took a typical load pattern of a North European country. In the IRES NGCC, there is 50% contribution of the renewables and 50% of the gas-fired power plants, which then has a capacity factor of 33%. And a similar for the gas CCS variant. And finally, we have a system, and this is based on a study, a German study, which used detailed power system simulation modeling at an hourly level. And this system included a lot of wind energy. The capacity of factor of wind is lower, 33%, than in the other systems. This is because part of the wind energy is used to power the storage, and part is just curtailed. Here you see the part which is curtailed. This system was based on pumped hydro storage only, and according to the power system simulation modeling, this system would be feasible. This is then the comparison of the system cost, or the LCOE of the whole systems. I want to show you the CO2 emissions of the different systems, and those are in the black diamonds. You see that the system with the normal gas-fired power plants, the gas or the emissions are still quite high, 175 kilograms per megawatt hours, while in the other systems they always are below 50 kilograms per megawatt hours. Then I focus on the last two bars. That is the ones in cost in 2040. And you have the system with IRES and gas CCS and the system with IRES and storage. You see that they are, well, the last one is a bit more expensive. On the other hand, it is based on wind offshore, which is cheaper than the PV. So if the system would have included more PV, the costs would have been higher. Also, it's based on pumped hydro storage, which is not easily available in each country. So if you would have needed more battery storage, then also the cost would have been higher. In all systems, the cost ranges are, or the error bars are quite large, but increasing with increasing IRES and storage. So that brings me to the last slides. Of course, there were caveats in the study, and we are going to do more research. We especially missed projections on deployment of storage capacity in the different global energy scenarios. All reports said there would be a need of storage capacity, but they did not quantify the amounts or specified which technologies would be used. It would be required to have more power system simulation models which also model the power storage at an hourly basis. In this study, we did not include demand-side management and the impact on the load pattern. And of course, some techno-economic data are uncertain, especially for the novel technologies like the batteries. And progress ratios were for only a few based on historical time series. With this in mind, we can conclude that cost of gas CCS as backup is less than the batteries. Well, note that these costs are in relation that the charging costs are not included, and well, they are less uncertain. Under medium conditions, they are a bit higher than pumped hydro storage and compressed air, and lower than the batteries. And then finally, the cost compared of gas CCS as baseload. Again, less reduction than for IRES, because gas CCS, or the gas combined cycle part, is also more mature. It is also less uncertain, and then under medium conditions, excluding cost for IRES backup, they are in the same range as offshore wind and CSP and lower than PV. We found, we showed also in the graphs that it depends quite a lot on the deployment rate and also on the geographical locations. If we include the cost for backup services, well, then a system with gas CCS as backup, the costs are a bit lower than the one with pumped hydro storage. Okay, thank you. This is how I want to conclude my presentation.
Okay, thank you, Martel, for that excellent and informative presentation. We've received a number of questions that have been coming in through the presentation. Though in the time we have left in the webinar, around about half an hour, we'll be you're more than welcome to submit more questions through the box that you can see on the screen through the webinar control panel. Martel, let's start with a question from the audience. Why was simple gas turbine plus CCS not considered among your backup systems?
Yes, Niels, could you answer this, or you thought about it?
Yes, can anyone hear me?
Yes.
Okay. Yes, interesting question. One of the reasons is that simple cycle gas turbines already have quite a low efficiency, and equipping them with CO2 capture units would really reduce their efficiency further. Another practical reason why we did not include it is that most of the literature that investigates CO2 capture with gas turbines focus on combined cycles and not on simple cycles. So for practical reasons, we also had to exclude it.
Okay, thank you. Another question, what is the basis for the 14.5% discount rate that's been assumed for the natural gas combined cycle CCS case?
Yeah, okay, again, Niels, I think we found a specific publication which looked at the different specific discount rates for the different technologies. In most of the, by the way, most of the costs we showed now, there was a general discount rate of 10% for each technology to compare it more easily, and then we also had one sensitivity analysis, but I did not specifically focus on this one where you show the effect of the specific discount rate. Maybe Niels, you will have more information on this?
Yes, as Machtel just mentioned, as a default, we use a 10% discount rate, real discount rate for all the technologies. However, we also studied in sensitivity analysis what the effect would be if you would use technology-specific discount rates. And we took these discount rates from a special report that investigates discount rates per technology. And these discount rates were based on interviews with financiers and experts, and kind of reflects the uncertainty in the technology, which was perceived to be very large for CCS. And that was the main reason why we used such a high real discount rate. And the same holds for several storage technologies, which are also deemed to be quite uncertain.
Thank you. What size of natural gas combined cycle plant in megawatt terms did you assume?
Niels,
Yes.
Yes.
Yes, actually, we did not use one particular size. The data for the NGCC plants apply to net capacity sizes in a range of 420 to 910 megawatts without CO2 capture, and 350 to 800 megawatts with CO2 capture. So the uncertainty or the range in the values that we use also reflects differences in sizes.
Okay. What was the reason for not including power cost of charging the storage systems in the analysis?
The reason was for the LCOEs is that it is not known. You really have to look at the system. What would be those costs? There are now moments in time the power is just for free or negative cost, and there are moments when you would have to pay something. In a future system, the cost to charge power would probably be higher, but you can only look at that in a system costs way. So that's why we did the system analysis. And well, to do it in the LCOE as such, that would be such a range. It would not have been based on something. I don't know, Ed, do you have something to add to this?
No, I think basically you have a conservative assumption in this case. If the power charges had been added and if they were positive, it would make the cost of those storage technologies even higher than they were in this case.
Okay. Did you calculate what carbon price would be required to make your scenarios happen? This is if you assume that power plant builders build the most commercial or the cheapest solution.
Well, we didn't. You are asking if these. We did not make specific our own scenarios. We based our or we used the scenarios of others. So I don't quite understand the question.
Okay, we'll move on. There's another question about CO2 price. The CO2 price is very low at the moment, 5 to 6 euros. Was this considered in the CO2 price projections?
Well, we used the price projection of a scenario in which there was a good climate policy which could reach the 450 target, because we think that only in these kind of scenarios it's useful to look at this combination of IRES and gas CCS. In this case, we did not look at cost developments in other scenarios, business as usual ones. For the as a base price for we started with 13 euros per ton, and those costs we used to show the maximum cost reduction potential. Maybe Ed has to add something to this.
Martha, I was thinking in response to the previous question, I don't have the numbers offhand, but you did calculate some cost effectiveness, especially an avoidance cost number, which is, I think, effectively the kind of number that the question was asking for the four stylized scenarios. Which have different costs, but also different levels of CO2 emissions. If you or Niels can dig out those numbers, my recollection is that they were in the neighborhood of $100 per ton of CO2 avoided, with a range of different technologies.
Ed, we're having a little difficulty hearing you. If you could come a little bit closer to the microphone, that would be fantastic.
Okay. Is this better?
Thank you.
Is this better?
Yes.
Yes.
Okay. No, I was saying that in the draft paper there were some calculated values of cost effectiveness or cost of CO2 avoided for the four stylized scenarios, which have different costs but also different levels of CO2 emissions. And those would be the kind of carbon prices I think the previous question was asking about. I don't have those numbers.
Okay. Yeah, I have those.
Probably do. Yeah.
Yeah, I have.
$100 a ton.
I have these numbers indeed. If that was the question, then the cost of only the NGCC-CCS system would be like 87 to 57 euros per ton around, and the cost of a system with IRES and gas CCS as a backup system, they would be around, well, decreasing from 150 euros per ton to 125 euros per ton. And then we have the cost for an IRES with as backup storage system. Those costs would be the highest, and they would be around 240 euros per ton to 160 euros per ton CO2.
In 2040, is that right?
Yeah, that's right, yes.
Thank you. We've been asked in the future whether you plan to include coal with CCS and or nuclear power in your comparisons.
Yes, we are going to do a next study, and in this study we will include all the other technologies which are in these global scenarios, and to see then the full costs of the system. In this study, the scope was still limited. Yeah.
Does the conclusion that you've reached suggest investing in natural gas combined cycle with CCS for backup service?
Well, if you look at the cost, then it is certainly an option. Also, because the uncertainty is lower. If you want to do a bit more risk-free, then I think it would be a good technology to provide backup services as well. Ed, what is your thinking about this?
I was going to say, and also for baseload, I think one of the key messages here, which has not been prominent in discussions of CCS debate, is the relevance of CCS not only to coal but natural gas. To a large extent, CCS has been associated almost exclusively with coal, and particularly in a world where natural gas supplies might turn out to be much more plentiful than we thought as few as a few years ago. And looking at the requirements for carbon reductions that are consistent with climate mitigation scenarios, an increasing focus on CCS or natural gas plants, I think is the key take-home message. The Peterhead project that has been recently announced in the UK is really the first major demonstration plan for CCS on gas. Investments in CCS on gas plants and demonstrations of that are, I think, an important take-home of this analysis.
How much of the cost variability was from the cost of transport and storage?
I have to. Do you know this by heart, Niels?
Yes. Did you ask for the variability in the cost for transport and storage of CO2, right?
Yes.
This was 3 to 11 euros per megawatt hour, and this range is based on several conditions for CO2 transport, as well as the storage of CO2, which can also differ per site. And of course, there's also some uncertainty included.
Did the study address the availability of a sufficient amount of?
We did not particularly look at that. The German study, it was the system we looked at that was based on an assessment that it would be feasible. Later on, I think the author doesn't think this particular system will be realized with so much offshore wind, but the potential is there. It's just that in this form, it probably won't be realized, but the potential is there. We also looked at potentials for example, pumped hydro storage. There was a study of GRC, and this says there is quite a lot of potential in Europe, but the problem is more that it's use it. Do you have something to add or Niels?
No.
The 40% capacity factor for backup systems, one of our correspondents noted that seems quite high. Did you consider a lower capacity factor?
Yeah, I think in the stylized system there was, you saw indeed that the capacity factor of then gas was lower. It was 33%. I also think that the chances as backup, it probably will be that gas CCS of 40% is at the high side. If you take a capacity factor of around 30%, then probably the cost would increase by 15% around. So I think, yeah, that is right. It's at the high side. But the cost increase, yeah, will be around 15% if you take 30% capacity factor.
Okay. Why did you not select onshore wind to compare with?
Well, I think also onshore wind is important, and the cost reductions are probably are less. I looked at also a study of the International Energy Agency, and there the amount of doublings is 3 times, while for offshore wind this was many more times. I don't know by heart, 8 or around that. So we just chose 3 IRES on which we focused the results. I think onshore wind should be done also in the next phase. But the cost reduction potential is more limited, and that's why we chose the other technologies in the first instance. Niels, you have something more to add here?
No, I agree with that. Yeah, that's a point for further research.
Why did the CO2 compression unit, why were the CO2 compression unit costs considered separately from the CO2 capture unit?
Yeah, shall I answer that question?
Yes.
Well, this is for practical reasons that in the detailed literature studies that underlie our cost data, they present it as different components. So there's a practical reason why we did it in this way. And for that reason, by disaggregating it, we were better able to compare different cost studies. So that was the main reason.
Okay. What was your source of investment cost data for capture systems?
I have to look it up. Give me 1 second. Perhaps we could go to the next question, and I will refer to this question later on.
We can do that. Why is the learning curve of solar PV so steep compared to the other renewables? Is there a fundamental reason for that?
Shall I answer that, Machtel?
Yes.
This has to do with the fact that PV is produced in much higher numbers than the other technologies. Therefore, there are more doublings in the cumulative installed capacity, which result in much more cost reductions. The fact that the progress ratio of PV is much lower, or in other words, the learning rate is much higher for PV compared to other systems, is mainly or most likely due to the fact that PV systems are modular in nature, and this makes them more amenable to learning than other technologies, because it's more of a standardized unit, and these tend to learn faster in the production than other systems, for instance NGCC plants, who are more complex and therefore less susceptible to learning.
All the technologies that we talked about have capacity limitations due to public acceptance or distance from the shore. Have these been included in the doublings, these issues?
You meant, or in the scenarios, they envisioned these kind of potentials globally, and in these studies they also looked at constraints of the different IRES technologies, for example. For offshore wind, that in the Global Energy Assessment report and also in the Energy Technology Perspectives report, they did quite a substantial assessment of the different potentials of the IRES technologies.
Is this a good time, Niels, to go back to the question around the source of investment cost data?
Yeah, thank you. I was about to interrupt you. Yes, the CAPEX values stem from studies of the IAGHG, which were quite detailed, as well as the study from Parsons Brinkerhoff, as a UK study, and the zero emission platform. On a related note, I would like to say that we used the cost structure or the white paper of Rubin to structure the cost of all the technologies to make sure that we are not comparing apples and oranges, but structure all the costs of the technologies in a similar fashion. However, I should say that this was not always possible due to insufficient data on the structure of the costs in the sources we use for the data. But in general, they are all structured in a similar way.
Okay, thank you, Niels. I'm going to draw things to a close now, and by thanking our participants and thanking our panelists. If anyone still does have questions they would like to ask, please submit them to the Institute through the webinar inbox, which is webinar@globalccsinstitute.com. Just by way of a quick reminder, the webinar today has been recorded and it will be made available on our website in the next few days, along with the slides used. So if you did come in late or have colleagues who you think might appreciate seeing the webinar, we can make that happen for you. Lastly, as we are leaving this session today, we put together a very quick 3-question survey. And as you depart, we would really very much appreciate you taking the time to complete them to help us improve our ongoing webinar program. This is the latest in a series of webinars that the Global CCS Institute presents on all aspects of carbon capture and storage. And I'd certainly recommend that you keep an eye on our website to discover what further webinars may be presented. I certainly hope that you found this webinar valuable today. And once again, I would like to thank our presenter, Machtel van den Broek.
Yes, thank you as well.
Professor Edward Rubin.
Thank you.
And Niels Berghout for being part of our presentation today.
Yes, thank you very much.